Now see here, diffraction due to a single slit. So we are going to discuss the experimental study of the diffraction. So we have done actually what is diffraction, and we have seen the spreading of the light through an aperture. But now here where the maximum intensity is obtained, and what is the width of that, it means complete experimental study is done by using this experiment. For this experiment, suppose I have taken here the source of light, that is S, that here a lens is placed, convex lens, and this source is at the focus of this lens. So the rays coming or the wave coming from here are like this. After refraction, these wave will become parallel to each other. So we can say we obtain here a plane wavefront, that is PWF. Now this wavefront is made to fall on slit AB. This is A and this is B, and this is the unblocked portion of the wavefront. Now according to Huygens principle, each and every point of this wavefront acts as a new source of the disturbances or the new source of the light waves. So first we consider the waves or the disturbances which are emitted from this wavefront having the path difference 0. Suppose these are the here the radiations coming out which has got the path difference 0. Now another lens is placed over here to converge all these to converge all these waves at a point. When these waves gets converged at here, fall on this lens, gets converged at a point, and at this point we obtained maximum intensity. So this point is known as here the central maximum. Why the intensity is maximum? In the starting I have told, since there is a here the path difference 0, so constructive interference take place because of these here the waves coming from the portion of the wavefront. So we can say that due to the mutual interference, due to the mutual constructive interference, we get intensity maximum at the point this. This point we can take as, so that is known as central maximum, and on either side of this point we will be getting the bright bands but of the weak intensity. It means intensity will keep on reducing. So this is about the diffraction pattern. Now we can take the another point which are either side of the the central maximum. Suppose you have taken two waves which are at an angle here, at an angle theta here. It means they are not having the path difference 0 theta. After refraction through this lens, it means this lens is only used actually to convert these beams. So after refraction, these rays are suppose going to meet at this point P. We do not know what is happening at point P, whether it is a maximum intensity or the minimum intensity. So for studying this, we consider here, we draw a perpendicular from here, that is called AN. When the perpendicular is drawn, this angle is also here theta. So we can write BN is here path difference. If the width of the slit is suppose A, from here to here, that is A. So we can write A is here width of slit, then we can write here Bn is equal to A sin theta. So at the point P, whatever thing is found, whether it is the maximum point or the minimum point, that will depend on the path difference, and that is the path difference is here Bn. So now we have seen this, the Bn is the path difference. Suppose this Bn is equal to lambda. So if I take Bn is equal to lambda, that is the path difference. So in this case we can write Bn is equal to twice of lambda by 2, that is the even integral multiple of the half of the wavelength. In this case, we divide wavefront AB into two equal parts, AC and CB, and this one is a perpendicular here. So this is N. So now this wavefront AB is divided into two equal parts, AC and CB. So there are two independent sources of the light waves, one is AC and one is CB. This is lambda. So this is here lambda by 2. So all the corresponding waves or the disturbances emitted from AC and CB has path difference lambda by 2. It means one wave from here and one wave from here, one wave from here and one wave from here. These will have the path difference lambda by 2, and we know it, when the path difference is lambda by 2, phase difference will be coming here 180 degree and destructive interference will take place. So, if the path difference is here the lambda Bn is equal to lambda over here, in this case at the point P, we will be getting here the point where the intensity is minimum because of the mutual destructive interference of light, and this point is known as first secondary minima or the first secondary minimum. This point lies either side of the central maximum. So, in general we can write here path difference is equal to here A sin theta n is equal to n lambda, where n is equal to 1, 2, 3 like this. So, for all these path differences we will be getting the point where intensity is minimum, and we can name them like the first secondary minimum and second secondary minimum. So, now we have seen conditions for secondary minimum. Now, let us see the conditions for secondary maximum. So, suppose path difference Bn is equal to, I have taken 3 lambda by 2, that is odd integral multiple of half of the wavelength. In this case, we divide the slit AB into 3 equal parts like C, and here we can take D. So, here there are actually 3 equal parts on the wavefront. So, these 3 parts are acting as a new source of the disturbances. So, the light waves coming from any 2 corresponding parts will have the path difference lambda by 2. So, the 2 corresponding parts of this wavefront will be destructively interfere and intensity they will be giving 0 almost, but one part will remain uninterfered, or we can say unused. So, because of the third part which remains unused, we get some intensity at this point, and this point is known as first secondary maximum. It means that at this point intensity will not be 0. So, this point is known as first secondary maximum, that can be either side of the central maximum. In general, we can write here Bn is equal to A sin theta n is equal to 2n plus 1, that is here lambda by 2, and n equal to we can take 1, 2, 3 like this. So, for all these path differences we will be getting secondary maximum. It means first secondary maximum and second secondary maximum, third secondary maximum on the either side of the central maximum. So, this is the experimental study of the diffraction due to a single slit. So, we have seen the conditions for secondary minimum and conditions for secondary maximum. Now, we will see the intensity distribution here. Now, see, this is the graph between intensity and path difference. We can draw also with the phase difference. So, here this point is here, this is the central maximum where the intensity is maximum. So, this portion is known as here the central maximum, and this one is known as first secondary minimum on either side of the central maximum. This is the second secondary minimum like this. This is the first secondary maxima, this is the first secondary maxima. If you look at this picture, you will get it. On the either side of the central maximum, intensity of the maximum keeps on decreasing on the either side. So, this type of the intensity distribution takes place in the diffraction pattern. Now, we will do here actually the width of the central maximum. So, the linear width of the central maximum and angular width of the central maximum. Now, these parts we have to do.